We are starting on page 185. We're continuing the second activity from our last video. We didn't finish the last part of activity 2, so we're going to finish that, get to activity 3, and then complete a little bit of talk the talk. So that's pretty much it. So last activity we were talking about these two people, Jack and Jill, and that they were walking. They're walking at a specific rate. It was 4 yards every 3 seconds. So to give you kind of a conceptual image of this, 4 yards is a little bit more than like how tall the class is in 3 seconds. So it took them 3 seconds to go that distance. As a unit rate is where we have the denominator of 1. So this says 4/3 of a yard per second. So that's about a yardstick and like a ruler lined up. So that's a little bit past like waist high. So in 1 second, it's that distance there above, a little bit above waist high. Okay, right. So that gives you a little bit of an idea of how fast these two people are working or walking. Anyways, so from this we talked about similar triangles. How if a triangle lies, if you can draw a triangle where the diagonal is the line, they should have the same exact ratio despite the size of those triangles. They're similar triangles, similar right triangles. But a key word here that is what we've been leading to is the word slope. Okay, so slope talks about the steepness of a line. It's written as a fraction. It is a ratio of the change in our vertical distance, so how much we go up and down, over the, I'll put this in a different color, horizontal distance, how much we go left and right. Now, I'm going to write off to the side, but typically we'll characterize as something else, and you'll hear this in your future math classes. The change in our vertical distance, this is what we call is our rise. And the change in our horizontal distance, this is how much we run. So we could just say slope is its rise over run. So this is going to be something that we constantly reinforce here. But this is saying that it's the same ratio despite any 2 points you pick on the line. The slope of line is always constant. Since it's a straight line, it's not getting, these two people are not walking faster, they're not walking slower, they're keeping that same ratio and rate in terms of time or distance per second. And then we'll also talk about varying types of slope, but it says the sign of the slope indicates the direction of the line when the slope is positive. The graph increases from left to right. So that looks like, this is what we call as a positive slope. Versus when the slope is, let me put this in a different color, I'll put this in blue. When the slope is negative, the graph decreases from left to right. So a negative slope looks like this. Okay, so slightly different here. And then the convention to represent the slope by the variable. So we would use K for the constant proportionality. We use M for the slope. Now, it's kind of odd here. Why would we use the variable M to represent slope? A little bit of a history lesson here is because this is derived from the Latin word for slope, which is modulus. And modulus starts with M, and modulus in English means how much you move. So how much we move, right, makes sense if we think about it in that sense. So when you see M, think of how much you move. All right. Now we wrote an equation on the previous page to represent Jack and Jill. It is D equal to 4/3 times T. So every yard that they go, it's going to be 4/3 for every second. You multiply whatever second you have by 4/3. And we did that on a graph on activity 2 earlier. Okay, but let's go and represent number 8. It says let y represent the dependent variable. We know that. Although I'm highlighting here, just underline if you don't have a highlighter. And x is going to represent the independent variable. We always talked about dependent over independent, so it's y over x. But we're going to write an equation here. The equation to represent to represent the equation using y and x is y equal to mx. Right, so our Dependent variable is equal to, actually let's write that in here. Dependent variable is equal to our slope times, I'll put a dot there, times our independent variable. Okay, and then letter B, how is this equation similar to the equation of the constant of proportionality? We're going to say that those equations are the same. They're same. They're for the most part exactly the same, with one minor difference: the variable that we use. Right, for slope, I'll put slope here. It's m equal to y over x, and we know the constant of proportionality. I'll put COP, constant of proportionality. It's k equal to y over x. So we're noticing the differences there. Well, we'll talk later about, right, why do we use these different variables. But let's go and move on to activity 3, talking more about slope here. All right. So still working within the same context. It says in the previous activity, we're using the same equation, but now we have y equal to 4/3 x instead of d equal to 4/3 times t. And we have, we're going to be forming similar triangles where x is 1. So 1 second, 3 seconds, and 6 seconds. Now the graph for this equation is already, it's already graphed on the coordinate plane. Let's answer some things here. So the first question is this a proportional relationship? This is going to be something that you're going to see on your quiz next time I see you. So it'll be after this lesson. Is this a proportional relationship? We ask ourselves 2 questions. So first of all, it is a proportional relationship. But why is it a proportional relationship? This is of the form, we're going to say y equal to mx form. But it's because we have 2 things. Right, this blue line is a straight line, and it has to go through a specific point. It has to go through the origin. Right, so I'm giving you a big hint here. This is going to be involved in your quiz. So make sure that I don't know, put a star here, but straight line through the origin. I'll put the dot at the origin here. If it let's say it's a straight line, but it doesn't go through the origin, not proportional. Or it's a curved line, but it does go through the origin, also not proportional. It has to satisfy both conditions. All right, is the slope of the line positive or negative? This is a positive slope. There's actually 4 different types of slope. We'll talk about that later, but on the previous page, we said positive is represented as x increases, comma, y also increases. So let's look at the y and x axis here. The x axis, when x increases, it goes this way. I'm going to erase this though. Right, it goes to the right. And then as y increases, that's on the y axis, this is going up. All right. Now if you combine both of those directions, you get this type of diagonal line. That's a positive slope. I want go ahead and draw this line, but I'm gonna draw a stick figure here. This person, as they walk right along this line, their height is going to be going up. It's going to be increasing. If it increases, it tells us it's positive. If it decreases, that tells me it's negative. So that's a way you can tell. All right, but we're going to be drawing certain things on this graph. We'll be going back and forth. Let's go to number 3. Identify the slope between points A and B. So we talked about how this is the change in our vertical distance over the change of our horizontal distance, aka it's the rise over run. So it says create a right triangle using points A and B. Trace on padded paper, we're going to ignore that. But let's look at A and B. We're going to create a right triangle where we're connecting those points. I'm going to draw this first. A vertical line and a horizontal line. Okay. Now, it says on B, label a triangle with the vertical and horizontal distances. So we're going to count how wide and how tall this is. So how wide this triangle is, this is 4 units, right? 1, 2, 3, 4. And then how tall is this? This is 1, 2, 3, 4, 5, 6. If you need to, draw those arcs, but we'll put a 6 off to the right. Okay. C, it says labeled on padded paper the slope of the line between points A and B. We're just going to write it in the space. So it's, right, rise, which is 6, over run, which is 4. So vertical over horizontal, 6 over 4. Let's write that ratio. So the slope is equal to 6 over 4. Now this can be simplified. We practice this. We can divide by a common factor. We'll divide by 2. So this could also be characterized as this is a ratio of 3 to 2, or 3 over 2. I mean, you could write it like that. You could also simplify, like, what's half of 3? What's half of $3? You could also say that this is 1.5, right? $1.50. How that's kind of characterized here is, right, we're going up 1.5 and right 1 for every unit on the x-axis. Okay, now we're going to be still working with this graph, but the prompts are coming from the next page, on page 167. So let's get to that. Number 4, does the orientation of the right triangle matter? It's telling us to use patty paper. We're not going to use patty paper, but it still says use point A. Does the orientation, how I drew this right triangle, does that matter? I drew it like this. But we could also draw it in another way. I can draw this right triangle. I'll draw a vertical line and then a horizontal line this way. So we're looking at like this triangle here. Doesn't matter which way that I drew it, where I drew it underneath, and now I've drawn it above. I mean, it's still no, because if we count from A going up, 1, 2, 3, 4, 5, 6, we're still going 6 up. And if we go to the right, 1, 2, 3, 4, right, we still have 4. So it's 6 over 4, and just the work that we did, we know that's going to stay the same, right? Vertical distance over horizontal distance. So let's answer that question. Compare and contrast the two triangles. How are they the same? They still have the same ratio for the slope. Something that is slightly different here, right? How are they different? The right angle, the location of the triangle is switched, but we'll say the right angle is how we drew it. It was so the right angle was, we'll say, top left of the triangle. Okay, so the location of it matters, but we already know from rotations using transformations, right? If you rotate something, it's still the same exact figure. It does not change the orientation. If you spin, right, you spin yourself, you're still the same person. Okay. Number 4B, does the new triangle give you the same slope? Yep, we already answered that. It is yes. Right, we'll say same ratio. Right, still 6 over 4. It still simplifies to be 3 over 2, and we'll keep it like that as a simplified improper fraction. Now we're going to further explore this line with other points here. Number 5, it says create right triangles using points B and C, and then separately we'll go with B and D. It says trace it, but we'll leave it at that. So BC, BD, I'll try to remember that. BC, so B's right here, C's right here. Doesn't matter which way we draw it. I could go up and right. I'm gonna go right and up. I'm supposed to do that, and I'm also supposed to connect B and D. You know what? I'll go above the line for B and D. Let's go right here. We've got a lot of stuff going on here, but let's go back to this smaller triangle. I'll shade this. Let's count the side lengths, right? So from B to C, this is 2 to the right, and this is 3 up. That gives us a ratio, if we're looking at rise over run, still 3 over 2. Let's go to from B to D, this other one. And I'll draw this I'll draw my color horizontally. Let's count 1, 2, 3, 4, 5, 6. And to the right, 4. These are two similar triangles. They're the same shape but different size. This is going to be 6 over 4. If you divide it by 2, we've already gone through this exercise. It's the same exact ratio. So pretty much what this is saying, and we'll answer the question later, if you draw any right triangle on a line, you have the same ratio regardless. You should have the same ratio regardless, right? You should not have something different. If you have different numbers, it'll still simplify to be the same exact thing. So we're going to say from B to C, let's put, how do I want to label this? And I'll actually write it out. B to C, the ratio is 3 to 2. And then B to D, it was 6 over 4, but that became 3 over 2 as well. Okay, B, we already wrote this down, so we're going to skip that and go to C. How does the slope between these pairs of points compare to the slope of the original one that we got, A to B? Exactly the same. It was still 3 over 2. Okay, so this is what we what we call a constant rate of change. Keyword there is constant. All right, let's go to the next page, last part of activity 3. We're just going to kind of summarize these questions or these claims here. Number 6, compare claims that all right triangles formed using any 2 points on a given line are similar. Is Cooper correct here? So that's Cooper's claim. So this, we're going to say all the triangles have right angles. Right, so that they're similar. If you remember when we worked with angle similarity theorem, we had to prove that 2 of the angles are the same. So since they all are right triangles, they all have at least one angle the same. That is that they're right angles. So that's one. But another one that we can prove here, I'm going to put this in red. They also have corresponding angles here. So like this angle here for this big triangle corresponds with this one because that was from when we worked with parallel lines with the transversal. Those are corresponding. So we can say that they also share, let's go back. So all triangles have right angles, and then we also have a pair of corresponding CORR angles. Okay, so to prove this, it is because of angle we'll abbreviate similarity, SIM, theorem. Theorem is just a rule, which states if you have 2 angles that are the same, they've got to be similar triangles. And 7, what can you conclude about the slope of any 2 points on a line that you're going to get? You're going to, we'll say it results in similar triangles. But then also our second claim here is that you will always get the same slope. Right, as long as you, like, it would help to pick 2 good points on the line. Here on the graph, we already had points that we received from that. Anyways, let's go to, we're gonna go to talk the talk here. This just says on the back side of this paper, we're going to, so this is 189. We're going to create some type of graphic organizer. So if you go to the back side, we're going to do this very quickly because I don't want to make notes super long. Let's talk about these 3 things. Okay, so the slope. This talks about the steepness of a line. Right, typically the variable m. We use this in the equation y equal to mx. Right, it's the change of y over change of x. Oh, I forgot to say that. Whoops. So this is, let's put triangle y over triangle x. The triangle here is actually a variable. It means change of y over change of x. Okay, I forgot to mention that. Whoops. All right, anyways, let's go to the rate of change off to the right. This is, when you think of a rate, you can think of speed. So like miles per hour. You can think about distance per second. Like how much, let's say, food per lunch, like how fast you can eat, right? So it talks about speed there. Anyway, so we're going to put that this is the change of, so triangle, the change of the dependent variable over the, independent variable. This also talks about the unit rate. The unit rate is exactly the rate of change, with the exception of it has a denominator of 1. So what I mean by this is, let's say you go 60 miles in 2 hours. Well, the unit rate of that would be 30 miles per 1 hour. Okay, so an example of a rate here, we could say 4 yards every 3 seconds. That's not the unit rate, but that is the rate of change. But yeah, let's get to the unit rate here. So this has a denominator of 1. I'll put DEN of 1. So an example of this, let's put it was 30 miles per 1 hour, or you could put 30 mph. All right, and then constant proportionality is what we started with. This is the variable k, typically in the equation, y equal to kx, right? K does mean the same. It means the same as slope and rate of change. Same of slope. The only thing is that this is specifically for proportional relationships, so it's got to go through the origin. I'll put REL for relationships. And the last thing, I'm going to draw a teeny tiny graph of an example of a proportional relationship. It's just a straight line that goes through the origin. Okay, we'll end it there. All right, thank you.